Welcome, architects! Let's decode the financial mechanics of Amazon Bedrock and turn your AI applications into highly profitable machines. Welcome to a critically important module for any AI architect, decoding pricing models and cost optimization on Amazon Bedrock. Building incredible generative AI applications is a fantastic achievement, but if those applications are not financially sustainable, they will never survive in a production enterprise environment. Without proper cost management, API invocation fees can quickly spiral out of control. To understand how to optimize, we must first grasp the fundamental framework of AI architecture, the cost, quality, latency triangle. In any generative AI solution, these three factors are inextricably linked. You cannot optimize one without impacting the others. Quality refers to the accuracy, coherence, and depth of the model's output. Achieving the absolute highest quality often requires using massive, state-of-the-art models like Claude 3 Opus. However, utilizing these massive models directly increases your cost because they consume more computational resources, and it typically increases your latency because processing billions of parameters takes time. Conversely, if your primary goal is ultra-low latency for a real-time chatbot, you might select a smaller, more agile model like Titan Text Lite or Mistral 7B. This drops your latency and drastically reduces your cost, but it might result in a slight compromise in the nuanced quality of the complex reasoning. The secret to master-level AI architecture is finding the perfect equilibrium within this triangle for your specific use case. Throughout this module, we will explore the different pricing models AWS offers and uncover advanced strategies to maximize quality while keeping your latency and costs strictly within budget. Let us dive in. Mastering this balancing act is what separates good developers from great ones. Behold the golden triangle of AI architecture. Any adjustment to cost, quality, or latency inexorably shifts the balance of the others. Our objective is targeting the absolute geometric center for your use case. To optimize costs effectively, you must understand the two primary pricing models offered by Amazon Bedrock: on-demand and provisioned throughput. By default, Bedrock operates on a consumption-based or on-demand pricing model. In this mode, you pay strictly for the exact volume of data you process. How is this measured? It is calculated based on the number of input tokens you send to the model and the number of output tokens the model generates. This pay-as-you-go model is incredibly cost-effective for experimentation, development, and unpredictable workloads with spiky traffic. However, what if you are launching an enterprise application with massive, sustained, and highly predictable traffic? Or what if you need to deploy a custom, fine-tuned model? That is where provisioned throughput comes in. Instead of paying per token, you reserve dedicated computational capacity at a fixed hourly rate. Let us examine how we allocate this capacity programmatically using Python and the AWS SDK. Let's analyze the code required to secure dedicated compute resources via provisioned throughput. Using the Boto 3 Bedrock control plane client, we invoke the create provisioned model throughput API operation. First, we define model units. Model units are the core metric of provisioned throughput. They represent a specific allocation of underlying hardware resources designed to guarantee a consistent number of tokens processed per minute. Next, we specify a custom name for our provisioned endpoint and provide the exact model ID, which is the ARN of the base foundation model or our own fine-tuned custom model. What about the billing commitment? Provisioned throughput allows you to optimize costs by selecting a commitment duration. You can choose no commitment for hourly billing or commit to a 1-month or 6-month term for substantial financial discounts. A highly effective, yet often overlooked method for immediate cost optimization lies right within your API request payload. Because on-demand pricing bills you for every single output token generated by the foundation model, controlling the length of the model's response is a direct lever for cost control. How do we enforce this limit? By strictly configuring inference parameters like max tokens or max token count. If you leave the maximum token limit unbounded, a chatty model might generate a massive, verbose 5-paragraph response when all you needed was a single-sentence summary. You are forced to pay for all of those unnecessary output tokens. Additionally, by optimizing other parameters like temperature and top P, you ensure the model remains highly focused and deterministic, reducing the likelihood of irrelevant tangents or hallucinations that waste compute cycles. Excited! Let us review a code snippet to see how these limits are rigidly enforced during an API invocation. Let's break down this inference configuration. In this Python snippet, we are preparing a JSON payload to invoke the Amazon Titan text model. Inside our text generation config object, we explicitly declare the max token count parameter and set it to 150. This acts as a hard computational ceiling. Regardless of the prompt's complexity, the model is mathematically constrained to stop generating text once it hits 150 tokens. Why is this a best practice for cost optimization? Because it completely eliminates the risk of runaway token generation. If you're processing thousands of document summaries in a batch pipeline, capping the output length ensures your billing remains tightly predictable and within budget. We also set the temperature to 0.5 and top P to 0.9. While these parameters primarily control creativity and sampling diversity, a lower temperature forces the model to choose highly probable tokens. Amazed, this prevents the model from rambling, keeping the output highly relevant and concise. This process flow guarantees efficiency. The raw prompt hits our hard max token limit, is mathematically refined by our temperature and top P dials, and finally resolves into an optimized, budget-friendly output.
Now we are moving into the realm of advanced cost optimization strategies. One of the most revolutionary features introduced for Amazon Bedrock is prompt caching. In many enterprise applications, you send massive amounts of contextual data to the model repeatedly. For instance, you might prepend a massive system instruction, a complex set of formatting rules, or a large batch of few-shot examples to every single user query. Under standard pricing, you are billed for processing those exact same input tokens over and over again on every API call. This is incredibly inefficient and expensive. How does prompt caching solve this? Prompt caching allows you to explicitly cache the static, repeated portions of your prompt context. When subsequent requests hit the API using that exact same prompt prefix, Amazon Bedrock bypasses the computationally heavy input processing phase entirely. It simply retrieves the internal model state from the cache. The financial and performance benefits are absolutely staggering. By utilizing prompt caching on supported models like Anthropic's Claude 3.5 Sonnet or Amazon Nova, you can reduce your input token cost by up to 90%. But the benefits do not stop at billing. Because the model skips the heavy lifting of processing those initial tokens, your end-to-end inference latency can plummet by as much as 85%. Best practices dictate that you should cache the static instructions and few-shot examples while passing the dynamic user queries as uncached input appended to the end. You can even monitor your cache hit rates directly using CloudWatch metrics like cache read input tokens. Prompt caching is the ultimate tool for achieving low latency, highly sustainable, and cost-effective generative AI architectures. Observe the caching architecture. The heavy static prompt is stored securely as an internal model state, meaning only the lightweight dynamic user query needs active processing. Latency and costs absolutely plummet. What if you have millions of documents to process, and real-time latency is not a strict requirement? This brings us to another massive cost optimization lever: batch inference. In a typical synchronous API call, the application waits idle for the model to stream back the response. While crucial for chatbots, this is highly inefficient for background data processing tasks. Imagine a scenario where a marketing team needs to generate localized product descriptions for an entire catalog of 50,000 items. Firing 50,000 individual synchronous API requests would not only trigger throttling limits, but also maximize your on-demand token costs. So what is the optimized approach? You utilize Amazon Bedrock batch inference. Instead of immediate execution, you consolidate all your prompts into a single JSON-L file and upload it to an Amazon S3 bucket. You then trigger a batch inference job through the control plane, pointing Bedrock to your input bucket and specifying an output destination.
Bedrock absorbs this workload and processes it asynchronously, leveraging back-end compute capacity when it is most optimal. Because you are allowing AWS to optimize the scheduling and execution of the underlying hardware, AWS rewards you with a massive financial discount. Processing workloads via batch inference typically costs 50% less than standard on-demand pricing. Once the massive job completes, all the generated product descriptions are deposited neatly into your target S3 bucket, ready for integration into your database. For any background processing, metadata extraction, or large-scale document summarization, batch inference is the absolute gold standard for architectural cost optimization on Amazon Bedrock. It is an indispensable strategy for scalable AI. This offline processing pipeline is brilliant. We upload bulk data to S3, trigger the asynchronous job, and AWS handles the massive computational load during off-peak hours, returning a massive financial discount.
You cannot optimize what you cannot measure. Therefore, implementing robust monitoring and governance is the backbone of any sustainable cost optimization strategy. Deploying generative AI applications without strict financial visibility is a recipe for disaster. API invocation costs can quietly accumulate, leading to massive billing surprises at the end of the month. How do we establish this critical visibility in AWS? We leverage the deep integration between Amazon Bedrock, Amazon CloudWatch, and AWS Cost Explorer. CloudWatch continuously tracks vital operational metrics for every model you deploy. You can build comprehensive dashboards that visualize invocation counts, end-to-end latency, and, most importantly, the exact volume of input and output token counts processed over time. By analyzing these token counts, you can calculate your precise burn rate down to the minute. But AWS takes this a step further. You can enable Bedrock application inference profiles and attach cost allocation tags. This allows you to categorize your token spend by specific departments, projects, or even individual tenants in a multi-tenant SaaS application. Once tagged, this data flows directly into AWS Cost Explorer and AWS budgets. You can set hard financial limits and configure automated alarms. If your generative AI application suddenly experiences a spike in traffic and burns through 80% of your allocated monthly budget in a few hours, AWS budgets will trigger an Amazon SNS notification to instantly alert your FinOps and security teams. You can also utilize AWS Cost Anomaly Detection, which employs machine learning to automatically flag unusual spending patterns in your Bedrock workloads. Continuous monitoring ensures your AI initiatives remain profitable, predictable, and fully under your organization's control. Governance is fully automated here. Token data feeds into CloudWatch while tags route directly to Cost Explorer. If spending limits are breached, an SNS notification instantly alerts your security and finance teams. As we conclude this deep dive into pricing models and cost optimization, let us synthesize the architectural best practices that define a world-class generative AI deployment. True cost optimization requires a holistic end-to-end architectural approach. First, always apply the principle of right-sizing. Do not automatically default to the largest, most expensive foundation model available. For simple classification or routing tasks, utilize lightweight, cost-effective models. Reserve the expensive, heavy reasoning models strictly for complex analysis. Second, embrace event-driven and serverless architectures. By decoupling your application logic using Amazon API Gateway, AWS Lambda, and Amazon SQS, you ensure that compute resources are only instantiated when a prompt is actively being processed. This eliminates the financial drain of idle infrastructure. What about data retrieval? Implement Retrieval Augmented Generation, or RAG. Instead of feeding the model a massive token-heavy document, use a vector database like Amazon OpenSearch Serverless to extract and inject only the 2 or 3 most relevant paragraphs into the prompt. This drastically shrinks your input token payload, instantly slashing your invocation costs. Furthermore, isolate your staging and production environments using strict IAM policies to prevent developers from accidentally running high-volume tests against expensive production endpoints. By combining right-sizing, serverless orchestration, precise RAG context, prompt caching, and rigorous CloudWatch monitoring, you will architect generative AI solutions that deliver breathtaking innovation without breaking the bank. I hope this deep dive into decoding pricing models has equipped you with the skills to architect efficiently.
We invite you to like this video, subscribe to our channel, and visit quicktechie.com for premium, recently updated material as per the latest syllabus and certification prep, including Q&A banks, ebooks, audiobooks, full training, and interview guides. Follow this ultimate checklist to guarantee financial success. Right-size your model, orchestrate via serverless, shrink payloads via strict RAG, and govern everything with continuous monitoring frameworks.